Hello, everyone. Welcome to the Robotics Colloquium. We meet every Friday and have distinguished speakers speaking to us about robotics and AI. Today, I'm really excited to have Sebastian Castro. Sebastian is a roboticist and a scientist at what used to be called the Boston Dynamics AI Institute and is now called the Robotics and AI Institute, which also happens to be the name of the organization that I started at Amazon. So it's all very confusing. But it's a real pleasure to have Sebastian. Sebastian's done an incredible amount of work in robotics software engineering, robotics research, and also being able to showcase robotics to a much broader audience. I'm sure many of you have read his blog posts. My kids read them. At least I make my kids read them, and it's really fantastic. Sebastian's had a long and distinguished journey from Cornell to MIT to Boston Dynamics to Picnic to now RAI. I hope I captured most of those.
Right.
And really excited to have him. Sebastian will be here for a few more hours after this, so we'll have a little bit of time for questions and also perhaps for you all to meet with him. So take it away.
All right. Well, thank you for the introduction. Thank you for attending, and thank you all for having me here. It's exciting to be like a non-traditional guest in these settings. As Sid was saying, my background is mostly in the software engineering space, education, but also I've been kind of dipping my fingers into research. So we'll see how, I've tried to keep my hot takes to a minimum, but we'll see how that goes. So the title of today's talk is Implementing Robot Task Planning with Learned Manipulation Skills, which is a lot of words. Basically, task planning is a thing that exists. I'll give a little background on it, but I will talk more about the practical aspects of it, so hence the implementing, and then also kind of coming to terms with the new state of the art that's emerging, where machine learning is kind of ubiquitous in all sorts of different places in robotics pipelines. So to kind of illustrate some of the non-traditionalness, I will kind of rehash a bit of the introduction. But my academic background was in robotics, so I did my master's with Hadas Kreskazit. I was actually the first person to leave her lab because of the master's. And I worked on this project on high-level control of modular robots. This is a framework that Hadas had brought in from her previous work, where you go from a natural language specification to a linear temporal logic specification, and then you get these kind of guaranteed synthesizable controllers. This project was modular in two ways. One, it was a simulation versus hardware switch, but also modular in the sense that I was working with modular robots and how to adapt that morphology into this platform. So I learned a lot here about kind of my passion for System Z type engineering. So I really like this whole like composable pipeline going all the way from language to executing on robots, and then also the sim and hardware toggle was something that I've kind of taken with me the whole time. Professionally, again, I've been through all these places. The only thing I want to highlight here is that my professional background has spanned both the software engineering and not software engineering, industry versus academia. So I've got a lot of different perspectives, I think, that have brought me where I am now. In addition to that, I think, when I was at MathWorks, I started doing a lot of outreach kind of content in terms of making videos and educational material, and I kind of kept that going when I transitioned to software engineering in 2020. So you might have seen some of the stuff that Sid talked about with the personal blog and repositories, and I'm still kind of actively involved in the ROS community. So if any of you are in that community, hopefully I'll see more of your contributions there. Okay, that's enough about me. Let's talk about robots. So we know robots can perform these long horizon tasks. So if you have this natural language command like bring a healthy snack to my desk, the robot can interpret what all that means, and through some turn of magic, you get something like this that basically figures out a banana is a healthy snack. Is it? And it's one of the highest sugar fruits. I don't know. The robot already knew the banana was in the drawer, and it knows that it's going to my desk, which is that desk over there. So all of this is information that, for the purposes of this demo, was all manually injected, right? We had this very, basically pre-populated knowledge base that we had, and it's great. We know the robots can do this, but there's lots of opportunities for interacting more naturally with our robots. So I will spare you. I'll get to the part where the robot's closing the drawer, and then we'll move on. So how do we want to program robots? Whether you're working with a warehouse robot, one of these home service robots, or one of these academic robots masquerading as a search and rescue application, you basically have your nominal interface, which is low-level commands for your robot. But where we want to get to instead is to go to talking to a robot via what I'm calling high-level intent. So instead of going down to motor torques or things of that sort, we want to use more semantically meaningful inputs like named routines or high-level goals about the desired state of the world, or even kind of adapting to user preferences during the deployment of this robot. And generally, the kind of tooling that bridges this intent with low-level commands is referred to as deliberation. If you're interested more in kind of this very nebulous term, there's a nice survey paper here from Ingrand and Galab that basically talk about deliberation as a whole bunch of squares and circles that essentially provide some kind of isolation between the user's way to interact with the robots, via things like mission criteria or objectives or goal specifications, and these lower level ways of commanding the robot or even getting raw sensor input. So there's a lot going on here, and there's a rich history of kind of classical approaches to implement what is in the bucket of deliberation. So one thing that kind of keeps me awake is this deliberation in the age of learning, right? There's a lot of great manual engineering approaches, but now that learning is becoming more ubiquitous, you're kind of at this crossroads where if you go, I think, either extreme, you're probably going to have a bad time trying to kind of cover the gaps of the other extreme. So the general takeaway here is that I think if you're going with a fully manual engineered framework, then you probably can get a lot of robustness, but not a lot of generalizability. And I think industry still kind of biases towards this because even though there's a lot of kind of hand tuning and design work that goes in, at the end of the day, there's a lot of interpretability, debuggability, and potentially even the promise of formal guarantees with some of these approaches. But all that work generally tends to work only for very narrow problems. On the other hand, I think the learning is kind of the reverse of that, right? Where you have all these great approaches that are showing state-of-the-art performance on a variety of tasks under a multitude of conditions, but between things like data and compute inefficiency or demand for that, and that we don't yet have good ways to interpret these results, I think industry still has a little bit of hesitation towards getting into some of these approaches. So I would argue that what we're looking for, at least on our team, is this sweet spot in the middle where you have the magical, pretty castle that you can get to. And I think it's pretty intentional on my part that the road comes off of the manually engineered fork and not the other one, but that is very much my bias. Okay, so keeping this in mind, the talk is going to be focused on kind of giving a very quick background on task planning, talking about the traditional, and then more towards the direction of learning, and then just wrapping up with some concluding remarks. Okay, so rapid fire background for those not familiar with task planning. Generally, you have some world that contains entities, and if you can come up with some kind of model that you can use to search over, we call that planning. Very reductive and simple definition. But the key idea is that if you have something like this, where you have a desired state of the world that is not this initial state of the world, like the apple should be on the table, you might be able to come up with a task plan, which is a sequence of actions that the robot can take to basically to mutate the world from its current initial state to its desired state. So in this case, it's a pick and place operation. So you move somewhere, pick up a thing, move elsewhere, put down the thing. There's lots of domain-specific languages for this. The one that I'll focus on here is PDDL or PDDL, in which you essentially encode the set of possible abstract actions that your robot can take, and each action has its own parameters, preconditions, and effects that enable you to search. And all of these effects are based off of these Boolean values called predicates, which can be true or false, that dictates kind of what your successor function from one state to the other is during your search problem. So to give a very quick example, something like this might be as follows. If your goal is that the apple should be on the table and you have this conjunction of values as your initial state, you might start with that initial state and run your traditional breadth-first search, pruning out states that you've already visited before, because otherwise you get stuck in cycles. And at some point, you come up with a valid state that meets a specification, and you backtrack that, and that is your plan. Great. So yeah, this has been around since the 70s, if not before. This is nice, but actually planning too abstractly can have issues. So if you take the exact same planning domain, but with a slightly different tweaks on the world, you might have something like this, where it's exactly the same goal and exactly the same action sequence. However, if you try out something naively, you might get into a situation where that action is not feasible because you don't have any room in front of the table to put down this apple. Now you're at the point where, do you actually switch the type of abstract actions that you take? Or is there actually another plan within that meets that same template where you can actually swing around the hallway and put down the object at an open spot on the table? And how does this change if the objects are in different locations, if the door is open or closed? Does the robot know how to open and close doors? Do we have to augment our model with door opening and closing? There's a lot of questions there. So one pitfall really with these kind of high-level symbolic planners is this holy grail known as the downward refinement property, which is guaranteeing that if I'm doing this pick action, that when I run it on the robot, it is also guaranteed to work, which is like never the case. So there's been lots of ways to mitigate this, which I'm going to cover very quickly. Some de-risking strategies involve the whole camp that is called task and motion planning, or TAMP, which I'm very interested in. I would love to talk about it more, but not for this talk. But it's basically reasoning about the feasibility of motions at the time that you're planning the whole sequence of actions. There's also saying, you know what, my model is going to be wrong anyways, so I'm just going to have kind of like a model predictive control anytime planner, or whatever you want to call it, loop, where you're accounting for your modeling errors as you roll out your plan and you adjust. You might also kind of help guarantee this downward refinability by creating kind of skills that implement the abstract actions that are robust and reactive. This is kind of the very well-cited work on that front on sequential composition, where these skills are represented as these abstract funnels, where the idea is that if you have one skill that is able to kind of get to some stability basin that funnels well into another skill, then you can compose your different controllers. And lastly, I think involving humans is something very important. Like, if you have this task plan that gives you a sequence of like 100, 1,000 actions, it's not unreasonable to have a human kind of maybe give it a thumbs up or thumbs down, make a couple tweaks to the plan, either at the beginning of planning, or if something goes wrong, maybe the human can introduce more information to kind of correct the existing plan. And some work I'm pointing out here towards that is this notion of affordance templates, which I'll get to in a future slide. But the idea is that these are ways for humans to interactively modify their the plans that come out of these planners. So that's my whirlwind attempt at task planning. If anyone wants to talk more about it, we can do that later. So let's talk more about the implementing part. So you've got this framework, you have this magically beautiful sequences of actions, and you want to run them on a real robot. Concretely, that means that you need something that bridges that task planner up there with a more concrete execution layer that actually runs on the robot. So on the execution layer, particularly when you're working with these, you're working on these systems type contributions, you generally don't want to spend a lot of time on the execution side, and you want to, orchestrate things that already exist. So here's where I think, in my experience at least, having modular software systems, whether they're your own or whether you're using something off the shelf like ROS, it's generally very good to have a way to basically pull in lots of different heterogeneous components for fundamental capabilities of your robot, and then also have a way to get all those heterogeneous components to talk to each other via something like the ROS interprocess communication mechanism. So this has certainly been good in my experience, where you can pull from all these pieces to get stuff to work. But there's still something in the middle, which I've heard referred to as the magic cloud in some of the literature, where you need something that bridges between this task and execution layer. And this part is one where I've spent a lot of time on, where basically the things that implement those abstract actions can often benefit from something that helps you manage the complexity. And traditionally, this is done with this good old-fashioned engineering, which is another common acronym. But the idea is that you want to have some kind of representation of skills so that you can, basically have a good mapping between your abstract actions and your controllers. There's lots of tools to help with this. I think the two that have kind of survived the test of time, at least in industry, have been finite state machines and behavior trees. I think these are very ubiquitous in industry, maybe less so in academia. But the idea is that you have these kind of, instead of using plain code, you're grabbing something with a little bit more structure and formality behind it, so that you can, for example, interchange components or have more interpretability if you're trying to kind of visualize how your system is progressing through its task. So as far as behavior trees, has a really good textbook from Colloquium and Ogren, which also kind of contrasts behavior trees with other approaches. And then a presentation that I did last year with my colleague Andrew Stout also focuses specifically on behavior trees. So if you're interested in more background, there's things there, but I'll go through some examples of kind of how I've used behavior trees in the recent past. Yeah, so that was one direction. I think the other direction is going back down from the execution layer up to the task planner. Because we talked about the fact that your model is probably going to be wrong, there's going to be unanticipated issues wherever you go, you basically need some kind of world model, which is not the same world model as the learning community is using these days, but some representation of your world that communicates back any changes of state so that your planner can adapt accordingly. And there's again, different ways that you can implement this. But they do form what I call the glue of this planning framework, right? If you don't have anything that kind of gets a state back up to the planner, then you only have like a one-shot planner where you have to restart your whole demo for the next time you record a video, which is, again, doesn't really fly in some settings. So traditionally, these things are done purely through ontologies, which is a very fancy term for saying, I don't know, a relational database. But the idea is that all these objects that you're tracking in the world, like tables and objects on the table, you can just create these, kind of relationship mappings or even just directly reason in these Boolean predicates. But people try to also inject some kind of metric information into these databases. One work that I did when I was at CSAIL was it eventually ended up becoming this tool here called PyRoboSim, in which you have this kind of 2D floor plan with all the entities and similarly capturing the relationships. But you can also do some kind of basic motion planning within there. You can even go another level of fidelity or even go through a whole chain of levels of fidelity with things like metric semantic maps, where the same map that you can use for like your localization and mapping, you can combine that with some semantic information about the world and then kind of elevate things up to different categories like rooms or buildings, which you can also leverage for task planning.
Question?
Yes.
So whenever I've built world representations, one of the things that I've always struggled with, particularly world representations that are created by a sensor data, is the question of persistence. Like when you're not looking at something, is it still there or does it go away? Like, of course, this is very semantic. Like when you're not looking at a table, it's probably still there.
Yeah.
But when you're not looking at a bunny rabbit, it might have, hopped away. What's your perspective on that, and like how do these address it?
Yeah, I actually don't think this directly addresses it because this is why I drew the diagram as a feedback loop, right? The problem is that before you're executing an action, you need to go back and check whether your world model is still up to date, right? If somebody moves an object off of the table and you come back to it, maybe you originally thought it was there, but when you get there, you might want to do some kind of perception step to validate that the model is still true. And actually, this is where the reactive policies or behavior trees come into play. So this feeds really well, actually, into some of the next slides. Actually, just the one right after this. So this is one example of what the traditional workflow that we implemented at CSAIL, which I know that the flow of data is kind of weird, but you start at the bottom left there where you have a natural language query that gets converted into a specification that your task planner can understand. In this case, it is PDIDL. And then that sequence of plans goes through a mechanism to spit out behavior trees. And all of this, again, corresponds with your world model, right? So you have to do the planning with the current knowledge that you have about the objects that exist and where they are. And then you have something that executes. But like you said, Sid, it's not foolproof, right? So one thing that you might do is like once you have this kind of abstract sequence of actions, this might become a behavior tree that at the top level is just literally the same exact sequence of actions, right? You have a plan of 4 actions, there's a behavior tree of 4 actions. Great. But internally, each tree can be imbued with its own kind of reactive rules, right? So to answer Sid's question, for instance, the pick skill here, you might start the skill by first checking that the object that you're looking for is still there. If it's not there, then you actually fail out of the skill and presumably update your world representation, and then you have to go back to replanning. There might be cases where new information maybe doesn't really affect your current plan. in which case you can probably just proceed with your skill. But I guess one of the unsatisfying things, which we'll get to in the second part of the talk, is that it requires somebody to make these rules, right? Which is obviously a lot of work, and also something that keeps changing. But you could do something like this, and this is actually what we did at CSIL. So one example here is where we're trying to pick up the apple that's on the table, and the behavior tree is actually checking for the feasibility of a path to the apple and seeing that it can't find it, even though it sampled a bunch of grasps. So now it's decided to take a fallback route in the tree where it's going to pick up that green can, move it out of the way, and then once that object is placed out of the way, then the robot will go back and manipulate the object of interest. And again, in this case, we also did, whenever we did a pick and place action, we updated the location of objects for next time. So now we try again. We have a valid motion plan to the grasp, and the robot can proceed with its task. So going up a level, what we did for this work is we used Kaylin Garrett's work on this TAMP approach called pediddle stream, which is basically a regular solver that gets combined with sampling to actually instantiate some of the motion primitives in these actions. Let me actually play that again. So this was done using that PyRoboSim framework, or the precursor to, where we just had this. I was mostly just testing stuff to see if I could get a plan that made sense. And reasoning in this little simple 2D world is actually very useful as a way to check that the planner and the planning domain worked as we intended, that the robot was generally picking the right macro actions before we then kind of swapped out the low-level execution layer, and we're able to do the same kind of tasks in both a higher fidelity simulation and on hardware. And I apologize for the swinging Ethernet cable there. This is COVID times, and there was no one else there. But yeah, the idea is that if you make a system modular like this, you can actually take some of these purely abstract plans and just swap out some of the lower level components like your perception or your motion planning and get these working in the real world, which is very satisfying to show this at the end of about 10 months of work. Yeah.
One other question. Are there tools for verifying state charts? I mean, you're using behavior trees for like some of like loops and like other sort of known logical issues?
Yes. Are there tools for verifying behavior trees? Actually, yes. One of my collaborators on the open source side, Christian Henkel at Bosch Research, he and some colleagues of his have worked on this project called Convince, which is one of these EU grants, I believe. And they basically created a way to take these behavior tree representations, which are structured, generate them into a verifiable format, and then be able to do formal verification. That's another one of those things that these skill abstractions offer you. And behavior trees more so than state machines, because behavior trees are trees. They're acyclic. So you actually have a bit more structure that you can actually, I think with a state chart that could go, any two states can connect to each other, that gets a little more gnarly to verify. But certainly, and in the LTL to finite state machine world, there's also a lot of verification tools, which is something we've also done. Yes?
Like, quick follow-up. What are you trying to verify with the verifiers in this case?
I wouldn't speak for Sid, but I think what we're trying to verify is that the tree, for example, I don't know, for example, the robot never gets stuck in an infinite cycle, or the robot always makes sure that by the end of the behavior, the gripper will always be open no matter what you do. Like, these are kind of properties that you want. These typically...
Exactly. There are a bunch of sync states.
Yeah.
Either those sync states are failure states, or those sync states are successful states. You need to just guarantee that your traversal in finite time will actually get to those sync states. Like having written a lot of behavior trees and state machines, one of the challenges is you can make them loop around.
Yeah.
And this happens because you have partial information. It also happens because they're complicated to write. But yeah. One follow-up question between like behavior trees and state machine. I know you like one over the other. I love them both.
So do I.
One of the challenges I find with behavior trees is they get big really fast. State machines do too, but at least like you can like point one at each other and sort of get it to work. Like, is there Like, is there a way around that? Like, I find that sometimes to be like, when you have these schema-free databases, like NoSQL databases, like it sounds good in concept, but then you end up with like tons and tons of keys,
Yep.
and then it grows really big fast.
Yeah, so for managing behavior trees running away from you, I would say there's two things. One of them is actually a complete parallel to the state machine world, in which everyone was dunking on state machines for a while, and then all of a sudden this whole new concept of hierarchical state machines, wow, abstraction, came out, and all of a sudden people are like, you know what, this isn't so bad if we actually encapsulate things into functions. So behavior trees has the same concept of subtrees, right? The fact that you can manage your visual hierarchy without affecting the actual functionality is one way. The other thing is that I think with behavior trees, there tends to be a tendency to be maybe overly granular with what should be one behavior tree node. So I think just generally keeping behavior trees at a level of granularity where like the thing that is contained in a state or a node is something that you actually care whether it succeeded or failed. If you have a bunch of like very small things where you're like adding a number and then subtracting a number, like maybe you just package those together into one node. So you should, but it's an art. It's very easy to have trees that are either two, yeah.
One of the questions around like variable scoping, like is that like I know like I've faced this issue too quite a bit. Like do you want to pass complicated structures between each other, or you want to scope it the right way? Like again, like is there good guidance on that?
So this is interesting because behavior trees from like a theoretical perspective have a lot of nice things until you get to that situation where you're talking about, oh, we actually do have a global key value store. What do we do now? Exactly. And I think everyone just invents their own way to do scoping. And I think it is a little bit of reinventing the wheel, but the payoff I think is the visual hierarchy and the verifiability of the tree. So it's a design trade-off, I would say. At the end of the day, you could also just do this all with code. Yeah. Cool. So that's one approach. There's one more traditional approach that I want to talk about. And I know, Ashton, you were asking me if this was going to make it. It is here. So at Picnic, we did a NASA Phase 1 SBIR collaboration in which Ashton Larkin, who's a current student of Sid's, was part of, and he's the reason why I'm visiting here. But we were basically trying to bring some initial levels of task planning into our behavior tree-based product, right? So here we had an application where we're trying to transfer cargo. Think of like a lunar habitat or like space station application, where you want to get cargo in and out of storage depending on whether it's coming in or going out. And we actually ended up using an open source system called PlanSys2 in the ROS ecosystem to do this task planning, both in simulation and on hardware. This was really half of the project, in which we're basically trying to combine these like abstract task planners with some lower level skeleton-based motion planning. If anyone's familiar with Move It Task Constructor, we ended up using that. So it was kind of like a weird hierarchical TAMP framework. But we were able to achieve these tasks with relatively low clearance. Like opening that drawer was shockingly difficult for the degrees of freedom of that arm. But one of the other things that we wanted to do, and the reason that NASA was interested in this, is this concept of supervised autonomy. And what I mean is that you don't only have this autonomously executing skill in isolation, but you might actually want to involve a human in the pipeline. For example, if you have this long horizon plan, let's say it's 100 skills and you fail at skill number 51, maybe instead of throwing everything away, you might want to engage a user to do a teleop recovery. I think particularly due to the expense, both in terms of time and cost of having remote operators for space applications, it's okay if you have an operator that's intervening every now and then. So this is kind of the appeal. You basically have this little interactive marker where you can drag the robot to follow the instructions to recover from your task. And if you succeed at marking this as success, then the robot will proceed with the rest of its plan. Additionally to that, we were talking about the previewing earlier. So they were also interested in taking this another level where the behavior tree before executing the autonomous skill is actually running through a kind of a human-in-the-loop preview step where you'll see a preview of the motion trajectory, where the user can either approve or reject, and if they reject, they also get a marker to maybe adjust certain parameters of the motion. And this is really also driven by the work that I mentioned earlier on affordance templates by the folks at Track Labs, where they use this for both the Valkyrie you see there, but also for the DARPA Robotics Challenge, where they had these kind of motion planning primitives for doing things like opening valves or turning handles. And they would get an initial plan from perception and then adjust it on the fly. to actually complete their tasks. So this is another aspect of task planning that I think is worth noting. Now, one question in all of this is that I think all of these applications so far have been in the research space. So where does TAMP fit in industry? And I have two theories for why it's maybe not as present as we might want it to be, as I'm sure all of us here are TAMP enthusiasts. One of them is that industry is still focused on narrow, specialized applications. When I was working on the Boston Dynamics stretch, we were doing one thing and doing one thing really well, and that is taking boxes out of a truck. We could create the scripts ourselves. We actually enjoyed having the interpretability where we could, look at the logs, see exactly which state we were in, and be able to make modifications. And users also similarly wanted that transparency. That being said, there are companies that are using AI planning. A couple I've highlighted here are Magazino, which is a German logistics company that was also part of an EU grant called AI Plan for EU, in which they created their own Python-based system for task planning called Unified Planning, and they're using it for the robots. And on the more kind of modern side, you've got BotBuilt, which is a company based in North Carolina, I believe, in which they're actually ingesting floor plans of houses and using several foundation models to actually convert the floor plan into a PDDL domain for basically planning how to create the framing for houses. So they're focused on automating house construction. And this is a company that's led by a couple of folks, including my former colleague Barrett Ames, who's I think their CTO. It's one reason. The second reason is that implementing this stuff is hard. There's a lot of hidden work, maybe not so hidden because I've just spent 30 minutes talking about it, but especially as your problems get large, search can get expensive, especially if you're bringing in task and motion planning. Domain engineering is terrible. You have to kind of sit there and be an expert at PDDL or equivalent formalisms and get that right or not. And then even when you have the right plan, building all the infrastructure to track the execution, to recover from failures, and doing all that robustness is just going to be a lot of work. So I think, that goes back to the first point, where people are still focused on these narrower applications in industry until we make other things easier. So in all of this, how does learning help us? But at the same time, how does it help us while retaining the favorable properties of all these planning frameworks and behavior trees and whatever? So that gets into the work that we've been doing at Ray Institute on applying learning to planning frameworks. I will say that this section is more questions than answers, and I'm happy to chat about this more, so bear with me a little bit, but I think there's a lot of interesting stuff that hopefully I can incept into people's minds. So our team has basically started off with this work from one of our former interns, Deanne Wang, who made this equivariant diffusion policy. As its name says, it's what if diffusion policy, but equivariant. Essentially, we're using equivariant neural networks to exploit certain symmetries in the environment to help with sample efficiency. Besides that, it's pretty much the same thing. We're just able, I think this entire bagel baking demo that you see here was trained with something like 60 demonstrations. And the idea is that by having equivariance, you can now generalize to different positionings of the objects as long as they're symmetric about the point in the world that you specified. And that's great. We could also show this for other skills. This video will keep playing. But the big question is, all of this was still one demonstration. And that's true of other places, like the physical intelligence demos is also kind of one big demo of doing the laundry folding, for example. But we want to ask, how do we actually maybe chunk this up into different sub-skills and actually use them within a planning framework? So I'll talk a bit more about that. If we go back to our behavior tree example, but now all of our actual implementations are neural networks that do stuff, is it sufficient to learn a policy for each of these actions and we're good to go? Probably not, because we have 13 more minutes. So I'll talk more about that. Here's what we would like to have happen, right? You basically, in this case, it's learning from demonstration, right? We collect a bunch of demos for different skills, A, B, and C. We train individual policies to do that action. And then we can actually go through a task planner that knows about the existence of these actions, and we can get a plan. The plan in this case is skill A, B, and C. And if we kind of go back to our pictorial funnel representation, then A, B, and C happen to funnel into each other, and you can complete the task plan. But if you try a different combination of skills, like C, B, A, C, maybe you get into this situation where maybe the connection from C to B was barely enough to make it happen, and then you're just out of distribution. Even worse, because the reason we care about task planning is long horizons. So if we have something like this, I think we're out of luck with what we have here. So that's not going to work directly, right? There are really three challenges I highlighted here in skill composition. One of them is detecting skill termination. In other words, when does the funnel of one skill actually end? Second is zero-shot recomposition of skills. So if we reorder them, how do the funnels connect to each other? And three is generalizing to variations in the environment. In other words, can we make funnel bigger? And actually, this is true regardless of whether you're using learn policies or manual engineering. It just happens that if we're designing our own skills, then we can control that funnel by adding in all these rules. So it's not unique to that, but what we want to get to is if we've gone through the trouble of training policies, we don't want to fall back to then doing the manual engineering for composition of the skills. So that's really the question that we're asking ourselves. So challenge number one is detecting skill termination. We took the same bagel demo that I showed in the first video, and we essentially created a PDDL domain. We manually chopped up all the skills, trained, I think, 4 or 5 different policies, and tried to basically recreate them. I think at this point we had an operator that just clicked the button when the skill was done, moved on to the next one. And we were able to recreate it just fine. I think one thing that you see here, which I wanted to show specifically, is that because the policies have their own reactivity built into them, in this case, the robot first misses the bagel. And then at some point, when it comes time to update again, the robot will be like, oh, wait a minute, I should go back and pick it up. And this is all, again, contained locally within the policy, right? So we didn't tell the planner to do anything. But in certain cases, we might need to tell the planner that something went wrong, right? So can we detect when the skill is done, whether it's success or not? And can we detect when we can actually continue recovering versus where we're out of distribution and we should try to do something else? So yeah, when is a skill done? I mean, we've gone through the trouble of training this policy that takes in visual motor state and outputs actions. So can we also consider using maybe some of that same data? This is not necessarily the same network, but can we, additionally to predicting policy output, can we also predict completion, whether it's success or failure? In which case, it basically tells you, can you continue on with the plan, or should you kind of take a step back? Or can you instead classify the actual predicates or the truth values of certain propositions in the environment? In which case, you can actually validate how your state is predicted and how that compares against what you would have expected by the planner. So there's a couple of pros and cons of these approaches. I think on the left side, it's much easier to just label a Boolean success or failure or complete or not. But again, you don't really have much of that mechanism to connect to a planner. And I think the converse is true for the other side, right? Where labeling predicates lets you communicate state back to your planner, so you can do things like verify whether you can continue with your plan or abort and replan with a new known state. However, there's going to be a lot more data labeling, which we'll see in a second.
Hey, quick question.
Yep.
Is there a symmetry here in that, like here you're saying that finding the post condition for the skill is challenging? But I can imagine finding the precondition for the skill is also challenging. Like, how do you know when to initiate a skill? Like, because each skill has a particular domain.
Right.
Is that a problem for you?
Actually, I think it's an opportunity, because if you're on the left side, you need maybe a different classifier for the precondition and the postcondition. But over here, if you're labeling predicates, then you already get for free the information on whether or not you meet the preconditions or you've met the effects, right? Yep. So actually, it's appealing for that reason as well to have a predicate prediction. But like you're saying, Sid, that you can actually use the planning domain to convert between these approaches. So I'm going to talk about that. Let's say this is your demo, right? You're picking up a screwdriver and putting it down. One way to label is to label the skills themselves and use the symbolic domain to extract propositions. Meaning that if you just tag when a skill starts and ends, with some timestamp, you can say, well, I can just forward simulate my planning domain, and that tells me what are all the symbolic states as this system propagates. Forward simulating is one way. You can start with a known initial state and step forward. But actually, Toki Megimatsu and Jeanette Bogue, who I think is here next week, if not the week after, they have some work on doing it the other way, where they similarly use a symbolic domain, and they actually backward simulate and saying, well, based on what I'm seeing here, if I have placed a screwdriver, it means that I must have been holding a screwdriver before, so I can backward simulate only the propositions that I can be sure about. And then they also do some clever loss masking for only basically using the training data that they're sure about, because there might be some superfluous predicates that you don't know about. Like, it doesn't matter in this demo whether there was a wrench also on that table, right? So that's one option. The other option is actually to label the propositions and then extract the skills out of them, which has a lot of appeal, one of them being that you can actually more densely label your demo, because the previous approach basically assumes that your predicates only change at the skill boundaries, but that's not necessarily the case. However, a lot more labeling. You not only have, in this case, more time steps to label, but each label is individual proposition truth values instead of just a, yes, I'm done. So that's really annoying. Of course, this is where machine learning can help, right? So there's been lots of approaches to help automate the predicate labeling and or inference pipeline. So one of them is ask a pre-trained foundation model. Everyone loves this. So I think there's been lots of different levels of work. Some have proposed basically candidates, like pools of predicates that you can use for labeling. Some can help label the data itself. And others basically say, you know what, let's not even label or train a model. Let's just at runtime ask a VLM whether the screwdriver's on the table. And for simple tasks, I think that works. For more complicated, I don't know. The other option is to take, to actually learn from demonstrations. There's seminal work here called Skills to Symbols by George Kornidairis, which basically you demonstrate the skills that you're running, and because you basically have snapshots of the visual motor state of the robot when the skill ended and started, you can basically use learning to kind of come up with your own set of symbols that maybe don't have any semantic meaning because they're just determined by an algorithm, but you can use them for planning, and that's been great work. And there are systems that leverage both, right? Other approaches basically start with the candidate predicates from the top. So VLM spits out a bunch of data, and then you end up using this. In this work, I think they used a hill climbing optimization approach to whittle down that big initial list of possibly wrong predicates and only kept the ones that were relevant to the demonstrations. So you can either learn from data, whether it's data you collected or data someone else collected. I think it's the takeaway. So once we have all this machinery in place, the idea is that if you predict skill termination, you have a very simple behavior tree where you're basically at every time step checking whether your termination step predictor is true. And if it is, you keep executing the skill. And in the predicate case, you similarly have now basically checking whether your preconditions hold. What's happening here, if your preconditions don't hold, your skill fails. But if your effects are applied, the skill succeeds. And in both cases, the skill will also, terminate if the skill execution actually completes successfully. And then, if you kind of bring this all together, you might have this behavior tree where now you have these, policy and/or predicate classifiers that hook directly into the behavior tree. So you're just listening to what your model predicts, and that in turn, well, particularly the proposition truth values, can also in turn feed the outer loop of, having a task planner replan if needed, and then having the task executor manage which behavior tree you're running next. So this is what we're kind of building up to. Really quickly on a few other challenges. So these are some that we haven't been working on as directly, but another problem is with the skill recomposition, right? So here we trained those policies from our demo, and now we're trying to do a different combination of skills. And you see that the robot is kind of just tapping the tray, but not really closing it. This is really hard to determine, but this is happening because in the demonstrations, this sequence of skills was never done. So every time the robot had to close the tray, the gripper was actually oriented the other way. So the robot doesn't know what to do with the gripper turned 90 degrees, and it's trying to slowly tap the gripper while it's moving. And in this case, it just happened to work, but I think we just got lucky. And then eventually the robot is back in distribution and is able to continue with the plan. But generally, how do we handle these unseen skill compositions? A couple approaches here. One of them is just to collect a ton of data. You can never be out of distribution if you have infinite data. But other ways are to inject different types of inductive bias into your problem. 2 lines of work here that are promising. One of them is to actually interleave free space motion planning and policy execution. You can do things that are all the way from simple things like always move to home and always make sure your demos start at the home pose, which is not intellectually satisfying. And there's some work here I want to highlight from Brown. This is Ben Abate-Mateo, Eric Rosen, and all, that basically created this policy class called composable interaction primitives, or chips, in which the policy itself contains basically a value function for whether or not, for like a target pose to motion plan to, and then you switch over to a low-level policy. And this has been shown to show good results in these tasks that basically are marked by entering and leaving contact. Another way is to use object-centric representations. So you can get more sample efficiency if instead of using absolute poses of robots and or objects, you take advantage of affordances on objects or relative poses. This is basically another way to get equivariance without using actual equivariant neural networks. So we think this is promising. It can also help track skill initiation sets, I think. And lastly, we talked about generalizable skills. So we train a robot to pick up a screwdriver and put it down. But can we do these other alternative tasks zero shot? Probably not. What we want to get to is to go from having to train all of these as separate policies, collect 100 demos for each of these, like put screwdriver on shelf, put hammer on shelf. Instead, we want to go to a place where maybe we have a parametric skill that is conditioned by some kind of input based on the world, right? And this could take lots of shapes. These are just a couple of random ideas. Obviously, the one at the bottom left is a very cartoonish version of any VLM, but that's one that's shown a lot of promise, not necessarily the only one. So we think there's a lot here to basically reducing the number of total policies that you're training. So to recap, task planning and execution still has a similar framework with learned skills. You have a policy execution layer there instead of a generic execution layer. The idea is that you basically pull from your skill library, which is hopefully parametric. Your low level and your high level communicate via things like conditioning your policy on the downside, and on the upside having things like predicate classification or success classification. And you've got neurosymbolic planning tools at the top. Most critically, this is still there. To execute your policies, you still need a ton of motion planning and control and perception tools, both to actually make your arm move and to gather the right visual motor state for your policies. So that's not going away. And I want to make that very clear. Cool. So I'm going to do just a couple of concluding remarks, and then we'll have about 10 minutes for Q&A. So these are very text-heavy, because I mostly just want them to stay there for posterity. I'll be sending the slides for people who want. But one, I think that learning will let us break barriers in this deliberation framework, but the right ones. We have to pick the right barriers. So here's what I think we should keep, right? Maybe the most important is the top one. I think we should let calculators and not language generators actually do planning, particularly for long horizon skills. Language generators have their purpose in tons of other places in this pipeline. But additionally, there's lots of things like keeping track of symbolic state of the world, being able to communicate state to the user, and having these skill abstractions to help manage complexity that I think are still important. On the other hand, learning can improve a lot of important parts. We said domain engineering was terrible. If I didn't say that enough, I'll say it again. If you delegate a lot of the robustness to things like learned policies or learned value functions, you can keep the planning fairly abstract instead of having to reason about feasibility of motion planning, which is really expensive. And then I think more for the industry deployment side, I have the last 2 points, which is, I think one of the things about industry is that you make a solution and you need to have a field engineer, an application engineer, go on site and commission the system. So I think learning has a role in helping users, end users, commission systems for their specific operating conditions. And the only way you can do that is by deploying good enough models that you can bootstrap that process with, whether they're foundation models from up above, or you train your own foundation models. Secondly, the whole manual engineering versus learning conundrum. It should definitely be a with, not a versus. I think compositionality is still key, right? I think end-to-end learning has kind of had its heyday. We need to find other alternatives to help scale up. And I think basically the the less monolithic, the more modular you can make your system, you're just going to have a better time with doing, being able to switch directions and be an agile researcher. And to that point, also don't throw away good old-fashioned engineering. We have a lot of approaches that do work very well, things like inverse kinematics or state estimation or symbolic planning and verification, hypothetically. And so we should really apply machine learning to the tasks that we don't really have better answers for, is my belief. Finally, good tools for visualization, logging, and your ML data pipeline is going to make your life much nicer. So definitely have a good way to check whether the thing works instead of just, yeah, it ran. Cool. So I'll quickly wrap up. I think on robotics research and engineering, there's this fallacy that I think I was speaking to some people about, that robotics is really hard and complex, therefore its software must also be complex. That is not the case. I'm very happy to have heard from people here that also agree with this and have entire research thrusts in this direction, so thank you. Good embodied intelligence research requires a lot of engineering. I think anyone that works on these kind of corporate research entities will tell you about the value of having someone that can help wrangle robots. And lastly, even though this is all complicated, be accessible. I think you should be able to hang with the big wigs, but you should also try and make your work accessible to newcomers by practice your communication both to the experts and the non-experts. So that's my soapbox. Anyway, sorry to go a couple minutes over. Thank you for listening. We are also hiring, so I have to put that there. But otherwise, thank you, and I'm happy to take questions.